Hello, welcome to this new lecture of Math-S400, Mathematics and Economic Modeling. Today we're going to introduce some topology. In particular, we're going to talk about closed sets and open sets, and we're going to see the relationship between open and closed sets. Okay, so let's start. We have a set which is a subset of vectors, or k-dimensional Euclidean space. So let's start with the definition of a closed set. So we say that S is closed if the following definition holds. So for any sequence of vectors xn in the set, we have that if xn, this sequence converges to x, if this is true, well then, so this is an implication, okay, then the limit of the sequence, this vector x, should also be in the set. Okay, so for example, if this is my set S and I have a sequence, so any sequence of vectors in the set, so this could be x1, I could have an x2 and so on, right? So this is a sequence of vectors. If this sequence converges, for example, it converges to this vector x here, then the limiting vector should be in the set. Okay, and this should hold for any sequence of vectors in the set that you can think of. So this is the definition of a closed set. So let me give an example how we can use this definition to show that a particular set is closed. So for example, take the closed interval 0, 1. So we would like to show that this interval is closed. So how do we do it? Well, we take any sequence in the set. Okay. We take any sequence xn in 0, 1, and we assume that the sequence converges to some x. Okay. What we need to show is that this limiting number x is also in 0, 1. Okay. So how do we do it? Well, kind of make a small proof. So what do we know? We know that the entire sequence is in 0, 1. Okay, so if the entire sequence is in 0, 1, this means that for all n, xn is less or equal to 1 and xn is greater or equal to 0. Okay, that's the definition of the interval, closed interval 0, 1. And we also know that xn converges to the number x. So if you have a sequence of numbers and every number in the sequence is less or equal to 1, then by a previous theorem, a couple of lectures ago, we have that the limit keeps the inequality, right? Similarly, if you have a sequence of numbers and every number is greater or equal to some number, then the limit should also be greater or equal to this number. Okay, and then from this we immediately have that x is in 0, 1, which indeed shows that this interval is closed. Okay, so that's how you show that a certain set is closed. You take any arbitrary sequence in the set. If it converges, then the limit should also be in the set. Now let me give a second example of a set that is not closed. Okay, so let's take the interval 0, 1, but not including 1. Okay, so this is the line segment 0, 1. So here we have everything including 0, right, this entire thing, but except for the point 1 itself. Okay, so 1 is not included. So if you want to show that this set is not closed, well, then you have to show the negation of this. Okay, so let's first negate this. If you negate this, then you have, there exists a sequence right, that's the first part, and then we have to negate this, the premises. This is a P implies Q, so negating P implies Q is P and not Q. So we have the sequence xn converges to x, and x is not an S, right? So this is what we need to show for this interval. We need to find the sequence in this interval. The sequence converges to some number, but the limiting number is not in the set. Okay, so here you only need to generate one sequence in order to show that this is true. So it's easy to see. Well, the idea is that you get a sequence that somehow converges to the 1, right? This will be our limiting x, but then the 1 is not in the set. Okay, so one such sequence could be 1 minus 1 over n. Okay, so xn is 1 minus 1 over n. Then x1 will be 1 minus 1 will be 0. x2 will be 1 minus 1 half is 1 half. x3 is 2 over 3. x4 is 3 over 4, and so on. Okay, so if n goes to infinity, we have 1 minus 1 over n. This becomes really, really small, so this goes to 1. But 1 is not in S. Okay, so it's not in the, half open interval 0, 1. Okay, so this is a way to show that a certain set is not closed. So this is the definition of a closed set. Now let's go to the definition of an open set. So before we get to the definition, let me introduce some notation which will, I hope, make our life a bit easier. So let's take a number epsilon strictly bigger than 0, and let's take a vector x in Rk. Okay, and now I'm going to define the set B epsilon x, and these are all the vectors y in Rk, okay, such that the distance between y and x is smaller than epsilon. And this set here is called the open ball of radius epsilon around x. So why is this the open ball of radius epsilon around x? Well, if I have the vector x, then I need to find all the vectors whose distance from x is smaller than epsilon. And if I do this, what I need to do is draw a sphere or a ball of radius epsilon around x, and then everything inside this sphere, but not including the boundary, right? Because you have a strict inequality here. This entire green thing, this is B epsilon x. Okay, so this is this set that we have defined here. All the vectors that are epsilon close to x. Okay, now we are ready to define the notion of an open set. So let S be a subset of Rk, and then we say that S is open. The following holds. Well, for any vector x in this open set, I can find an epsilon bigger than 0, such that for all vectors y in this ball of radius epsilon around x, y is also in S. Okay. So for any element that I can find in the set, this basically says I can draw a ball of some radius, strictly positive radius, around this vector such that anything inside this ball should also be in the set. Okay, so if I have an S, then for any x that I can take, I can draw a ball of radius epsilon. Epsilon can be very small, but it has to be strictly positive, such that everything inside this ball here, this green, is also in the set S. Okay, so that's the concept of an open set. When I'm inside the set, I can move a little bit around, and wherever I go in this little neighborhood, I'm still in the set. Okay, so let me give an example of an open set. For example, the open set 0, 1, not including 0 and not including 1, is an open set. Okay, so if I draw this, we have 0, 1, and then in this interval is everything below 0 and 1, but not including 0 itself and not including 1 itself. Okay, so it's all the numbers strictly bigger than 0 and strictly smaller than 1. So we would like to show that the set is open, so it has to satisfy this definition. Let me put it in a box. Okay, so for any x and s, right, so I take any x strictly bigger than 0 and strictly smaller than 1, I can find an epsilon such that anything epsilon close to x should also be in set. Okay, so here I have to find an epsilon such that if I don't move further than epsilon away, I'm still in this interval. Okay, so I need to take my epsilon such that if I move epsilon, if I take epsilon far away, I'm not crossing the 0, and if I go epsilon away to the other side, I'm not further away from than 1. Okay, so for example, an epsilon could here be the half point between 0 and x and the half point between x and 1, but then take the smallest one of these two numbers. Okay, so here we would have epsilon x over 2, and here we would have epsilon 1 minus x over 2, but then take the minimum of these two. Right, this should still allow me to go epsilon far away but not cross the 0 or the 1. So let's show that this indeed satisfies this definition. Right, so I have taken an x, given this x I need to find an epsilon that satisfies this definition. Right, so I defined epsilon to be this. Right, epsilon can depend on x. Okay, that's for all x you need to find an epsilon, so the epsilon can depend on x. Let me show that this epsilon indeed satisfies this definition. Okay, so I need to show that for all y in, basically it's the open interval x minus epsilon, x plus epsilon, then y is also in 0, 1 in the set S. Okay, so in one-dimensional space, this here is the ball of radius epsilon around the number x. Okay, so if y is in the set, then I know that x minus epsilon is smaller than y is smaller than x plus epsilon. Okay, or in other words, you can rewrite this in different ways. X minus y is smaller than epsilon. Okay, maybe this is the easiest way. So if x minus y is smaller than epsilon, and epsilon is the minimum of these two, well, then I know that x minus y is smaller than x over 2, and x minus y is smaller than 1 minus x over 2. Right? It's smaller than both because epsilon is equal to the minimum. So from this definition, I know that y is bigger than x minus this epsilon, right? So it's bigger than x minus x over 2, and it's smaller than x plus x over 2. From this condition here, okay, I lost my camera. Okay, so from this definition here, I know that y is strictly bigger than x minus 1 minus x over 2, and y is strictly smaller than x plus 1 minus x over 2. So all of these conditions are satisfied. So in particular, if I take this one, then I know that x minus x over 2 is x over 2 is smaller than y, and x is bigger than 0, right? Because x is between 0 and 1. So I know that 0 is smaller than y. Okay, so y is at least bigger than 0. And then I can take this one here. From this, it follows that y is smaller than, so put this on common denominator, 2x minus x plus 1. So this is 1 plus x over 2. And x is smaller than 1. So this is smaller than 1 plus 1 over 2, which is equal to 1. So also y is smaller than 1. And from these two, it follows that y is in the open interval 0, 1. Okay, so this is a way how you can show that this interval is an open set. For any x, you find an epsilon, which might be a function of x, right? It might depend on x. And then for anything in the ball of radius epsilon around x, you show that it's also in the set S in the open interval. Now let me give a second example. For example, I consider the half-open interval 0, 1, and I would like to show that this is not an open set. Okay, so in order to show that it's not open, I have to negate this formula. So what's the negation? The negation, well, there exists an x in S, so here it's the half-open interval. And then for all epsilon bigger than 0, there exists a y in the ball of radius epsilon around x, such that, negating the premises, y is not in 0, 1. Okay, so let's repeat. I have to find a number in this interval, so that for any epsilon, I can find something in the ball of radius epsilon around x, such that y is not in the interval. So drawing this interval, I have 0, 1. These are all my points. I have to exclude 1. So I have to find an x on this green portion, such that for any epsilon, I can find something with epsilon distance from x, such that y is not in the interval. So here there's only one point that satisfies this, and that's the point 0. Okay, so set x equal to 0. Now for any epsilon, I have to find a y. Find y in, so x is 0, so this is now the open interval minus epsilon, epsilon. Okay, so this is 0 minus epsilon, and this is 0 plus epsilon, right? I have to find a y in this interval such that y is not in 0, 1. Okay, so for example, I can take y to be equal to minus epsilon over 2, and this is strictly less than 0, so it's not in the interval. Okay, so for any epsilon that I draw here, I can always find a y, something in this interval. For example, here this y, that's not in on the green portion of the line. Okay, so this is how you can show that a certain set is not an open set. So open and closed sets are related to each other. But let me first give some additional examples. So we already have seen that 0, 1 is closed, and 0, 1 is not, this interval is not closed. And we have seen that this is open, but this is not open, right? So these intervals are neither open nor closed, right? So it's not necessarily the case that if an interval is not open, then it's closed. So the two are not negations of each other, right? So you can have sets that are neither open nor closed, right? They don't satisfy any of the two conditions. Okay, so this is important. It's not because you have shown that the set is not open that it's automatically closed. Okay, but the two are in some sense related, and this is part of the following theorem. Its statement is quite simple. So it says that the set S is closed if and only if the complement of the set, right? And what's the complement? The complement is everything, all of the vectors except everything that's in the set, right? It's everything except. So S is closed if the complement, so this is the complement of S, is open. Okay. So here the complement of this set is all the numbers except everything between 0 and 1. So here the complement is everything between -infinity and 0. Okay, and then everything strictly bigger than 1. So this is 1, infinity. Okay, sorry, I cannot include 1. So because this is closed, the theorem says that this here, this union of two sets, is open. If you take the complement of this, then we have that everything from -infinity to 0 union everything from 1 to infinity. Okay, so if this is open, then this theorem says that this set is closed. Okay, and vice versa. Good, so let's try to show this theorem. So this is an if and only if. So instead of complement, I will also write this as S with a superscript C, right? Because every time writing RK minus S is a bit annoying. I will write the complement also as this. So we have an if and only if, so we have to go from the left to the right, and we have to go from the right to the left. So let's first go from the left to the right. And we're going to use a proof by contradiction. So assume that S is closed. So P implies Q, negating as P and not Q. So assume that S is closed and SC, complement of S, is not open. Okay, so let's use the mathematical formulas for closed and open. Okay, so S is closed, this means that for all sequences xn in S, if xn converges to x, well, these are vectors, then x is in S. Okay, so this is the first. The second, we have that xc is not open. Okay, so we have to negate the definition of an open set, as we have done before. So we know that there should exist a vector x in SC, right? It's SC that's not open, not S, such that for all epsilon bigger than 0, there exists a y in the ball of radius epsilon around x, and then this y is not in the complement SC. Okay, so that's negating the definition of an open set, right? This definition here, if we negate this definition, we get exactly this. Okay, so let's think about what happens here with the second one. I can find something in the complement such that for any epsilon, I can find something in this ball such that it's not in the complement. Okay, so let's take this x. Which is in SC. Okay, and then I know that for all epsilon bigger than 0, there exists a y in B epsilon x, such that y is not an SC, and if y is not an SC in the complement of S, then y has to be an S, right? If it's not in the complement, then it has to be an S. If it's not an S, then it has to be in the complement. That's the definition of the complement, is everything except for S. Okay. So what we're going to do, we're going to plug in different values of epsilon. So this holds for every epsilon. So we're going to plug in different values. We're going to get different y's. So basically we're going to generate a sequence of y's for different values of epsilon. So for example, if I take epsilon equal to 1, well then I know there exists a y in the radius, the ball of radius 1 around x, such that y is an S. So let me call this particular y, let me call this y1. Right, so let me call this y1. I can take another value of epsilon, 1/2. Well, I know that there's a y. Let me call this y2. This is now in the ball of radius 1/2 around x, right? My epsilon is 1/2. And I know that y2 is in s. I can take epsilon to be, let's say, 1/3. Then I know that there's a y3 in the ball of radius 1/3 around x, such that y3 is in s. And I can keep doing this for smaller and smaller values of epsilon, right? So at the nth step, I will have epsilon to be equal to 1/n, and then I know that there exists a yn in the ball of radius 1/n around x, such that yn is in s. And I can continue doing this basically forever. Okay. So using this procedure, I get a sequence, right? A sequence y_n's, right? So for every n, I get a y1, I get a y2, I get a y3, and so on, and so on, and so on. So this generates a sequence. And what do I know about the sequence? Well, for all n, the distance between yn and x, right here, the distance of yn is smaller than 1. Distance for y2 from x is smaller than 1/2. Distance from y3 from x is smaller than 1/3, and in general, distance from yn to x is smaller than 1/n. So this is smaller than 1/n. So if n goes to infinity, we know that this goes to 0. 1/n, the sequence 1/n goes to 0. So by the convergence lemma, we know that this goes to 0. So let me put it here. So I know that yn, this sequence, converges to x. So what do we know also about this sequence? Well, we know that y1 is in s, y2 is in s, y3 is in s. All of them y's are in s. So this is a sequence in s. Okay. And the sequence converges to x. But we had that s is closed, right? So for any sequence in s, if the sequence converges, right? So here y is a sequence in s, and it converges, right? Then the limit also needs to be in s. So from this, it follows that x is in s. However, this contradicts the fact that we assumed that x was in the complement of s, right? So it cannot be in both. So here we get the desired contradiction. Okay, so let's go over the proof once more. We said that the complement, we assumed that the complement was not open, right, by contradiction. This means that there exists an x such that for any epsilon, I can find something epsilon close to x that's not in the complement, right? So we take this particular x. Using this definition, we generated a sequence of y's that get closer and closer and closer and closer to x, and every element in the sequence was in s. Okay, so this generates a sequence in s, which we assume to be closed. It gets closer and closer to x, so in particular it converges to x. So because s is closed, this requires the limit here, x, to be in s, which contradicts the fact that we took x to be in the complement of s. Okay, the vector cannot be both in s and in its complement, so this gives the desired contradiction. Okay, so this is one part of the proof. S is closed implies the complement is open. So we also need to give a proof, let me go back to my blue pen, of the reverse direction, namely that if the complement is open, then S is closed. And again, we're going to do a proof by contradiction. So P implies Q, we're going to assume P and not Q. So we're going to assume that the complement is open, but S is not closed. So assume SC is open and S is not closed. Okay. So let's write again the definitions of open and closed, or open and not closed in this case. So SC is open. This means that for all x and SC, I can find an epsilon bigger than 0, such that for all vectors y in the ball of radius epsilon around x, it's SC that's closed, so y is in SC. Okay. And S is not closed, so we have to negate the definition of closed being closed. So we have that there exists a sequence xn in S such that the sequence xn converges to some x, but the limit x is not an S. Okay, so these are the things that we have, right? So for every x in SC there exists an epsilon such that for every y in the neighborhood around x, y is in SC. That's the definition of open. And then I can find a sequence in S such that the sequence converges to a vector, but the vector is not in S itself. So let's take this x here. So let's take the sequence, right? So let's take the sequence that satisfies this definition, right? So we have a sequence xn going to x, and we know that for all n, xn is in S, all right? There's a sequence in S, it converges to x, and we know that x is not in S, all right? This is from 2. If x is not in S, well, this is the same as saying that x is in the complement of S, right? If a vector is not in a set, then it has to be in the complement. Okay. So because S is in the complement, I know that this definition holds for this particular x, right? Because it holds for every element in the complement. Okay, so from this, from point 1, it follows that I can find an epsilon bigger than 0, such that for all y in this ball of radius epsilon around x, y is in the complement SC. So take this epsilon that satisfies this. Okay, so what's happening here? I have a sequence NS that converges to x, but there's some epsilon such that everything that's epsilon close to x has to be in the complement. However, this sequence is entirely in S, and at some point it has to be epsilon close, right? So if I take this definition here, well, I know that for all, let me now not call it epsilon because I already have an epsilon here, but I know that for every number strictly positive, I can find a number, natural number, such that for all n greater or equal to this number, xn minus x is smaller than delta. Okay, so this holds for all delta. So let's take this epsilon here and put it equal to this, or take a delta and let us put it equal to this epsilon here that we have found. Okay, so take delta to be equal to the epsilon that we have found here. Right, call this 3. Take delta to be equal to epsilon from 3. Then we know that there exists an n such that for all n greater or equal to n, xn minus x is smaller than epsilon. What does it mean for xn to be epsilon close to x? Well, this means that xn is in the ball of radius epsilon around x. So here we know that for all n greater or equal to this big N, xn is in the ball of radius epsilon around x. Here we have that for all elements in this ball of radius epsilon around x, this element has to be in the complement. So from this it follows that xn is in the complement of S, right? From 3. Okay. Now is it possible that this is in the complement of S? Well, no, because here I assume that every element in the sequence is in S. And here I have found some elements in the sequence that are in the complement. So here this is the desired contradiction. So let's go over it again. By contradiction, we assume that the complement is open, but S is not closed. This is the definition of being open. This is the definition of not being closed. In particular, there's a sequence that converges to some number, and the number is not in S. So if it's not in S, then it has to be in the complement, right? This is here. If it's in the complement, it's in an open set. So I can find an epsilon such that everything that's epsilon close to this number is in the complement. Right, that's the definition of the complement being closed. But then because this sequence converges to X, at some point it has to become epsilon close. Right? It has to enter this ball of radius epsilon around X. So at some point this sequence entered this ball, but everything inside this ball is in the complement, so the sequence cannot be in S. Okay, so that's the contradiction that we obtain here. So let's take a small break. So we have seen the definition of a closed and open set. And from the previous lectures, we have also seen the concept of a bounded set. Right, so remember that S is bounded if there exists a number, okay, such that for all vectors in S, the norm of X is smaller than M. And you have that S is closed. You have just seen this for all sequences xn in S. If the sequence converges to some vector x, well then this vector also has to be in the set. Okay, so this is the definition of bounded, and then we have the definition of being closed. If we have a set that satisfies both, right, so it's bounded and it's closed, then this has a special name, and then we say that the set is compact. Compact. So S is bounded and closed. So that's the definition of being compact. It's both bounded and closed. If it's bounded and closed, then it's compact, and vice versa. So what's nice about compact sets? Well, that's the following. So if S is compact, okay, then we know that we can use the Bolzano-Weierstrass theorem, and then we can say that, so let me start over. Let's take a sequence xn in some set S, right? And let's assume that S is compact. Okay. Then we know that S is bounded, right? So by the Bolzano-Weierstrass theorem, we know that this sequence has a convergent subsequence. Okay, so there exists a convergent subsequence. That converges, right? There exists a subsequence that converges. So in particular, we can, for example, assume that x phi n converges to x. Now the subsequence is also in S, right? So by closeness of the set, we have that the limit of this sequence, right, X is also in S. Okay, so if you have a sequence in a compact set, then we know it has a convergent subsequence, and the limit of this convergent subsequence is also in S, right? So basically, any compact set, any sequence in a compact set has a convergent sequence whose limit is also in the set. Okay, so that's the big advantage of being able to capture it into one definition, compactness. Any compact set, any sequence in a compact set has a convergent subsequence whose limit is also in the set. Okay, so this is an easy consequence of having the definition of closeness together with the definition of boundedness and Bolzano-Weierstrass. Okay. So before I finish this lecture, I want to give one more additional result. And this is the following result. So now let S be a subset of R. Okay, and here this is important that it's R and not RK, because I'm going to talk about the supremum and the infimum of the set. And the supremum and infimum is only well defined if you're talking about subsets of R, not if you talk about subsets of RK. Right? For subsets of RK, the supremum and infimum is not very well defined. Right? So here, this is important. I only look at S being a subset of R. Okay, so what is the result? So if S is compact, okay, so it's closed and bounded. Well, if it's bounded, then we know that the supremum exists and we know that the infimum exists, right? So the supremum of S exists, right? So I can talk about it. And the infimum of S also exists. Well, if S is compact, then it turns out that the supremum of S is an element of S, and the infimum of S is also an element of S. Alright, so I already told you that it's not always the case that the supremum and the infimum are part of the set. Right, so for example, in the interval 0, 1, the supremum is 1, but it's not part of the set S. However, if S is compact, so closed and bounded, then they have to be in the set, right? In other words, this cannot be a compact set because 1, the supremum, is not in the set, right? In order to make it compact, you have to make it closed, and you can make it closed by including the number 1 to the set. So let's prove this. We're going to prove it for the supremum. The proof for the infimum is very similar, so I leave it as a homework to make the proof for the infimum. So we know that S is compact, right? So basically this is, if S is compact, then the supremum is in S, and then the infimum is in S. So S is compact, so S is bounded, which means that sub S and inf S exist, right? So that's the first thing we need to check, otherwise this doesn't make any sense, right? You cannot talk about supremum if it doesn't exist. Okay, so next let Y be equal to the supremum of S. Okay, so Y is the number, it's an upper bound and it's the lowest upper bound. And we have seen an equivalent definition of supremum a few lectures ago, so let me recall what it is. So we know that Y is the supremum if it satisfies two things. Well, Y is an upper bound, and we call this UB, upper bound of S. And then the second definition says that for all epsilon bigger than 0, I can find an element X in S such that Y is smaller than X plus epsilon. Okay, so we proved this equivalence between these two a few lectures ago. So watch back on the video on supremum and infimum if you do not recall this result. Okay, and we're going to use this in order to show that the supremum, this Y, is also in the set S. So what are we going to do? We're going to use the definition to basically construct a sequence of elements in S that converges to the supremum. And then because S is closed, right, it's compact, so it's bounded and closed, then the limit of the sequence will also be in the set. Okay. So how does the sequence looks like? Well, basically we're just going to plug in different values of this epsilon, and they're going to become smaller and smaller and smaller and smaller. Okay. So, for example, if I take epsilon to be equal to 1, well, then I know that there exists an x, let me call it x1, in S such that y is smaller than x1 plus epsilon, and y is an upper bound, right? So I know that y is bigger than x1 minus epsilon, right? Y is greater or equal to x1, right? Because it's an upper bound, so if I decrease x1 by a little bit, I make it strictly smaller than y. Okay, so this is because it's an upper bound, and this is because, right? So if this is 1 and this is 2, this is because of 1, and this follows because of 2. Okay, I can do the same. I can take epsilon to be equal to, so instead of epsilon I can write 1, right, because epsilon is equal to 1. So let me do this here, minus 1, and here plus 1. I can take epsilon to be 1/2, then I know that there is an x2 in S such that x1 minus epsilon, which is now 1/2, smaller than y is smaller than x1 plus 1/2. I can take epsilon to be equal to 1/3. I know there's an x3 in S by this definition here, such that so this should be x2, sorry, x3 minus 1/3 smaller than y is smaller than x3 plus 1/3, and so on and so on. Okay, so after n steps I put epsilon to be equal to 1 over n, and then I know that there's an xn in S such that xn minus 1 over n is smaller than y is smaller than xn plus 1 over n, and so on and so on. Okay, so I can continue doing this indefinitely long. As a result of this, I get a sequence of numbers x1, x2, x3, x4, and so on and so on. So I get a sequence xn in S. All of these elements are in S. And xn minus y, right? The distance between x1 and y is smaller than 1. Distance between x2 and y is smaller than 1/2. Distance between x3 and y is smaller than 1/3. So in general, the distance between xn and y is smaller than 1 over n. Okay, and this 1 over n converges to, if n goes very big, this converges to 0. So by the convergence lemma, we know that xn minus y goes to 0. So xn converges to y, which is equal to the supremum of S, remember, and because S is closed, right, S is compact, so it's bounded and closed. S is closed, we have a sequence ns that converges to a number, so the limit also has to be in the closed set. And we have shown that indeed the supremum of S is also in the set. Okay, so this is the final thing I have to say on this video. I hope to see you soon again.